Okay, hi. My name is Bryn Brankamp, and welcome to the Voxel File channel. This is a channel where I am creating a foundation layer for making a video game. And I'm using Rust, of course, and when I left off in my last vlog about this project that I'm working on named Hexane, I was making the graphics pipeline in Vulkan terms. And it would be probably better if I showed. So when I left off, I showed you this line right here, creating the graphics pipeline. And I'm going to explain everything between creating the pipeline compiler all the way down to creating the buffer today. These are the things that I've implemented since my last video. So essentially what the pipeline compiler is an object which contains all the information about all the pipelines that have been created. It also contains the information needed in order to load and hot reload shaders at runtime. At compile time, I can specify what sort of compiler I want to use for the shader, under what sort of conditions I want to be able to hot reload, under the source directory and the asset directory. This is all figured out at compile time, although the directory themselves is figured out when the program is executed. So if I go into where I have the pipelines, I scroll up a bit, I have some sort of, let me find it, pipeline compiler info right here. So I have some sort of shader compiler, the source and the asset directory, and then just the debug name, which is used for debugging purposes, for throwing errors and the like. And you can see that the pipeline compiler is not too much different than the info. It also contains the shader, the source, the asset directory, and the debug name. And this structure is used to create the graphics pipeline. This was the function that I had left off last time. And there are a couple requirements for this function. So first I need to define a shader. And a shader has a type. And I just brought the shader type, all the types, into scope, so I can just say it's a vertex or a fragment shader. And then I specify what file the shader is in. And if you can see right here, I'll just pull this to the side. I have a shader file which has both the vertex and the fragment shader in it. And you can see if vertex is defined, then we call this main function, and we also define this positions array. And in the case that fragment is defined, we define some sort of results, which is the color that will be outputted to the screen at any given pixel, and the function main, which at this point just returns red. And let me slide this back over so I can show you the function in which I'm actually creating the graphics pipeline. So the graphic pipeline info is a structure which takes some shaders. It takes the attachments, the information for the color attachments. That's just the the picture that will be shown to you on the screen, or some picture that I have off the screen that I'm using for some sort of computation. It also has the picture information for the depth buffer, and what the depth buffer is for any given pixel on the screen, I might have it very far away or I might have it very close, and it just represents the closeness of the things on the screen. And this is going to be useful for some optimizations that can be done by the GPU. It also has information for rasterization, which is the process of converting the points that are provided, the vertices, into the triangles and then into the pixels that are on the screen. And I won't go into push constant size. I've already said what the debug name is for. And essentially this is provided to the create graphics pipeline function. I'm doing some destructuring here of the pipeline compiler and the device that I get from the pipeline compiler in order to just bring the logical device for Vulkan and the descriptor set layout into scope. And I digress because I would like to talk about descriptor set layouts. And where I create the descriptor set layout would actually be in the context, because the context creates the device. And essentially for descriptor sets, as far as they go, if you understand the Vulkan technical jargon, I have one. My entire API has one descriptor set. And what I'm doing is I'm allocating a large number of descriptors for each descriptor, for just the single descriptor set. And what I'm doing is I'm going to index into those descriptors in order to get the images and the buffers I need. That is the pictures on the screen that I'm going to be using outside of the one that's actually on the screen. And the buckets that I put the different blocks, I put the different data, if you will, into. Basically what this is saying is that there's only one place. Is that what I'm saying? It's not the place so much, but it's saying there's only one configuration for which the information will be laid out. And that's just being provided that I have 64 samplers, 64 images of the sampled variety, 64 images of the storage variety, etc., and 64 of the storage buffers. And that's interesting. They can be used in the vertex and the fragment shader equally. And this descriptor set is used for all pipelines. And the API just keeps track of the different buffers and images as they pertain to the different pipelines and the different descriptor sets. All of that is handled under the hood in what is called a bindless architecture for this API. Furthermore, if I go back to the main.rs, you can see that I'm providing the shaders and the color information, and the rest of this, and this should actually be format swapchain.format, because this is the what this is saying is that this is the format of whatever the display, whatever the screen that you're looking at right now is in, as the GPU wants it to be. I hope all this is making sense so far. Let me know, leave a comment down below if my technical explanation in this format of video works for you. Furthermore, or moreover, after destructuring all this information, I compile the shaders. And so basically I create an input path and an output path, which includes the file name and extension. And then I compile to SPIR-V using the compiler in the pipeline compiler. And this compiler, don't be fooled, is actually the shader compiler. And the shader compiler is very interesting. Essentially, I have a case where I have no shader compiler, and that's also the default. I have GLSLC, which is one of the compilers provided by the Vulkan SDK, as well as DXC, which is the DirectX compiler. And I believe that's also provided by Vulkan, but I have not implemented DirectX compiler yet. But in the case that there is no compiler, we just read straight from the output path. It's essentially the SPIR-V that's in the asset directory. And we just convert this to SPIR-V that can be used later. And in the case of using GLSLC, what I do is I just invoke GLSLC. It's very simple in that way. And essentially what this is doing, the very interesting thing that's happening here is I read the shader right here. I read this code here, and then at this line right here, what it does is if we're compiling the vertex shader, it will essentially add a line and then define vertex. And in that case, this block of code gets run. And in the case of the fragment shader, it will add the line define fragment, and then this block of code will be run. And in the case of a compute shader, it will also define compute. and then it writes that modified shader code to a temporary path, and then it invokes GLSLC on that temporary path. It loads the spurv from GLSLC, it passes on any errors from GLSLC to the program, and then it removes the temporary path, and then everything should be written out to disk, and it should also be provided to the program. So that, and what I don't have yet is checking if something was last modified inside the program's lifetime such that I can hot reload the shaders. Hot reloading is not yet fully implemented, but it should be fairly easy to implement. Hot reloading just means if I modify the shader code, then it will automatically load that shader code back into the program and continue executing seamlessly with the modified code. After compiling the shader into spurv and then getting that spurv, what I do is I just convert it to, I basically send it to the graphics card, the instructions to the graphics card so that it can be used later. I do some cleanup with the results that I get from this vector. This is basically a vector of results, and then I return those results from the function if they're an error. And then I just convert the shader data as provided from here, which basically is just the type of shader and the module, and I use that to construct the pipeline shader stage create info, and that's just a structure which the pipeline uses to understand all the shaders that are in the pipeline. Interestingly, I'm not using any vertex input state, or vertex inputs, that is. And the reason why is because for all the vertex information that I'm using outside of the actual vertices, what I'm going to do is I'm just going to have a storage buffer, and then I'm going to use GL vertex index right here. I'm just going to use this in order to index in very much like how I'm indexing into this array. I'm just going to use a buffer to do that. After specifying that, I specify that I have a list of triangles, so we have not pairs, but triplets of points. So we have a tuple of 3 points, each the first, the second, and the third in a counterclockwise, I think is the default way, specifies a triangle, and then the fourth, the fifth, and the sixth points will specify another triangle, and so on and so forth. And then I convert the rasterization data as specified earlier into a format that the Vulkan pipeline can use. And an interesting thing about this is for the depth and stencil state. I don't think I have stencil in my API, but for the depth state rather, if any depth state was provided, then I enable depth testing. And in the case that it was provided, I convert that information into a format that the Vulkan pipeline can use, or I just convert it into the defaults if there is no depth information provided, and then I just fill out the structure with the converted information. And I do a very similar thing for the color attachments for the format and the blending states. That is how the colors are combined in the pictures on the screen. I do a very similar thing for the color attachments. And then I'm just compiling all the color attachment information together. I'm specifying that I have the viewport, that is like the resolution, and the scissor, that is where in that resolution, where in that space that you provided in the viewport we're actually drawing. I'm just saying those are dynamic, so they're specified when we draw. And then I'm just using that descriptor set layout I used before to create the pipeline layout, and that's, like I said, it's just how the information is going to be internalized by Vulkan. And then I just create the graphics pipeline, and I return a struct which contains the pipeline, and then a reference to the pipeline compiler, and then the pipeline compiler has a reference to the device, and then the device has a reference to the context which contains the instance. the Vulkan instance that is, so that I can appropriately destroy things when their lifetime has been exceeded. And the other interesting thing that I've done is I've also implemented buffers. So I will quickly go over how I'm creating buffers. So in device, I essentially have this function which takes a buffer info and then returns an opaque handle. This is the interesting part, an opaque handle to a buffer. And what an opaque handle means is that I don't own that information. I don't have the information, but I do have a number that represents that information. So think of a deli line. Everyone pulls their ticket and then they wait to be called upon. Or in this case, they can also go to the counter and say, here, I have this number. Can you give me my order? Can you give me the meat that I had asked for from the deli? That's what an opaque handle means, if that makes any sense. And as for the buffer info, it's nothing too special. It's just how the memory is used, how the buffer is used. This is basically saying, is it a list of points which I'm drawing to the screen? Is it the order in which those points are drawn to the screen? Is it some arbitrary information? Or is it, if you imagine the bucket analogy, and I have a bucket of water and I want to take that bucket and put it into another bucket, is it the source of that information that I will be transferring the water from one bucket to the other? Is it the source where the water was, or is it the destination where the water is going? And that's just what the usage is. And I'm doing some destructuring here, defining some variables, just so that I can create the buffer. And this is the buffer as it pertains to Vulkan. And then I get the memory requirements, which is just basically saying how big is the buffer, and not where it is in memory, but it's the alignment. So it's the offset. So is it offset by 2 in memory? Is it offset by 4 in memory? Powers of 2, by 8, by 16. Usually it's 64 for different things in Vulkan. I've found things have to be aligned to every 64. So if I have a million numbers, then the points will go from 0 to 1000. And then the indices don't go at 1000. They don't start at 1000. They will start at 1024 because that's a multiple of 64. And that's what the memory requirements is. It just basically allows it to be in a format that the GPU will like. And then I get the properties of the graphics card as it pertains to memory. This is just what the graphics card can do. And then I do some technical jargon in order to allocate or to ask for the buckets from the graphics cards. I can say, can you give me a bucket in which I can put the information into? And then the interesting thing is I combine the buffer, which is not necessarily the bucket. The buffer is it's like saying I will have a bucket, but the bucket is in a box, and the box has a specific color, and that color can be generally 2 different things. It can be the color of a buffer, which is some arbitrary information, is what I'm saying. The bucket contains arbitrary information, or it's an image, so it contains pictorial data or pictorial information. So basically something that can be displayed on the screen, or something that can be used to display something on the screen. And then the interesting thing is that I'm basically storing the Vulkan data in the device for my API, and then I'm just returning the opaque handle. So it's just the number that I can have for the device. So in the shader, what I'll do is I'll say I have buffer number 3, and buffer number 3 has all the information that I want. So I'll ask for buffer number 3, and then I'll get that actual buffer. So I don't actually own that buffer, I just know the number which represents that buffer. And that's the same for images too. All in all, this is a really great first step. I'm really just so excited for this API, for what I've been working on. I think without Gabe Runlet and Patrick's help, I wouldn't have been able to get this far. This is really a great iteration on top of what I've done in the past year, the different graphics programming that I've done in the past year. And I think this is going to be a foundation. I'm at the point where I can create a foundation that I can use forever, that I can use indefinitely into the future, and just keep improving on the same thing instead of going on to the next project and going on to the next project. This is something that I can truly use into perpetuity. And I really love it if you use it as well when it's done. But it's not done, so I won't get ahead of myself. If you liked this format of video, me going over the technical information of how I'm using Vulkan behind the scenes, feel free to let me know in the comments. But besides that, that's all for what I have today. Thank you so much for watching Voxel File. My name is Bryn Brankamp, and I hope you have a wonderful rest of your day. Bye-bye.